Hello, welcome to iTelescope, and today we have Kormu, who is a PhD student at the University of Helsinki. She's a theoretical physicist in the third year, and she's going to tell us all about the early universe.
Okay. Can you see my mouse before I start, if I want to point at things?
Yes, we can. We can.
Okay, brilliant, brilliant. Thank you. So, good Friday, everyone. I'm going to talk to you about bubbles, strings, and other quirks in the early universe. Without further ado, let's jump right into our first question. If I could get the poll.
Okay, 1 second. Let me just find it.
Problem.
Give me a second. I didn't expect to be challenged so early. Wait a second. Polls, here we go.
Yes. So what are cosmic strings? I give you 4 options. A, they are very dense line-like objects, or B, a string theoretical object, C, a strand of cosmic yarn, or D, topological defects. There are multiple correct answers here, so don't be afraid.
Okay, good. Well, we'll leave them a bit of time. See if everybody gets their head around this, because it's not a topic you deal with every day. So.
No, I assume not.
Okay, so we got another, give it another 20 seconds. By the way, thanks for reminding me to record. I nearly forgot that. It's good. Okay. Okay, we'll give another 5 seconds and then. Yep, I will share the results. What do you think, Anna?
I kind of assume that the string theory one would win, but I'll come back to this later. I do love that people voted for option C, which was personally my favorite, really. A strand of cosmic yarn. I can tell you already now that that's, of course, not the case, unfortunately. As much as I would like to knit something from that yarn, it doesn't exist.
Okay.
But let's start this actually. So I'm going to talk about the early universe. So I guess the first question really is, how early is early? Well, the answer is shortly, very early. So I'm going to talk about times roughly 10 to minus 12 seconds immediately after the Big Bang and even earlier. The Big Bang is in quotation marks because physicists are terrible at naming things, and the Big Bang is a bit of a bad name, but what I really mean is after the inflation has finished. So this is also one of the reasons why physicists usually talk about energies when they talk about really early stuff, because it's much easier for us to understand what sort of like energies we are talking about and what sort of temperatures we have around that like time after the Big Bang. So I'm going to talk to you about cosmic strings and bubbles today mainly, and then I have 2 other smaller quirks that I chose. So here you can see at 10 to minus 12 seconds after the Big Bang, which is 0.11 zeros and then 1 seconds after the beginning of time, essentially. And the other thing that I'm going to talk about is cosmic strings that are roughly at 10 to minus 34 seconds after the Big Bang. So really, really early stuff. For reference, the first light, so the cosmic microwave background that you can see here, is at 380,000 years after. So there's quite a lot of time where lots have happened. And then finally, years after that, we get the first light from the universe. And the reason why I'm talking about these 2 events specifically is because they could source gravitational waves that could be actually detectable still today in the form of a gravitational wave background. However, let's first recap certain things. So I'm going to go through 3 things: gravitational waves, phase transitions, and then one is actually a ground state of energy before we jump into these exciting events in the early universe. So I'm sure that the previous webinars have also talked a lot about gravitational waves, and so on. But I thought the little recap never really hurt anyone. So we are going to start with gravitational waves. So they are ripples in space-time, and space-time is a 4-dimensional object. And because it's a bit hard to understand, because we live in a very 3-dimensional world, we usually draw it as a grid. And this grid then is easy to understand how the gravitational waves affect things around us and so on. So if you have a massive object, such as this pink-ish ball here, it creates this dent in the space-time. And that is the effect that it has on gravity. The gravity pulls the net or the grid down, creating the dent in it. So how do we then actually get gravitational waves? Well, usually we need 2 massive objects, such as these 2 balls here, orbiting around each other and causing these ripples and disturbances in the space-time. So they are created when massive objects accelerate, for example. And maybe the most famous example of such things in the universe are black holes orbiting around each other. They are very massive objects, so it's a very violent event in the universe. And that is what we need for a gravitational wave that we could actually detect. If you go and dance about, sure, that will create gravitational waves, but unfortunately, or fortunately, we are not very massive. So the gravitational waves that we would create would be tiny, and we would never hope to detect them. But gravitational waves from black holes are something that we can feasibly detect. And eventually these 2 black holes will then collide and merge together, forming one happy black hole. And gravitational waves are predicted by general relativity. That is the famous theory that Albert Einstein came up with in 1916. But Einstein himself actually changed his mind multiple times if gravitational waves were actually a thing or not. At first, he thought that they might just be a feature of the theory, but not actually a real physical thing. But here you can see in the rather disturbing oscillating cylinder tube how a passing gravitational wave stretches and squeezes space. So you can see that in this direction it clearly stretches, but here on this vertical one it clearly squeezes the space together. So really short history of how we actually detect gravitational waves, or what we have attempted so far. So the first detectors are from the 1960s. They were these like huge aluminum bars where the idea was that they would resonate with the frequency of the gravitational wave when one passed us. Unfortunately, we never saw anything, or rather heard anything. But the first indirect detection actually comes already in the year 74 in the name of Hulse-Taylor binary. Hulse-Taylor binary is a neutron star and a pulsar orbiting around each other. And so a neutron star is a core of a collapsed star. It's very dense. And a pulsar is a neutron star that spins rapidly and emits electromagnetic radiation. So we can actually see the radiation when it points towards Earth. They are sort of like this cosmic lighthouse in the space, and I think they're really cool. So this binary here, they orbit around each other and they were losing energy. So they were getting closer and closer together. And the system was losing energy exactly as general relativity predicted it. And we could observe that. So that was the first indirect evidence that we had that gravitational waves are actually a real thing that we might be able to observe in the future. And they got the Nobel for it in '93. We did have to wait almost exactly 100 years for the first direct detection. So the theory predicted them in 1916, and the first direct detection came in 2016 by LIGO, which stands for Laser Interferometer Gravitational Wave Observatory. And I'm going to talk a little bit more about this laser interferometry towards the end of this presentation, but they got the Nobel for it in 2017. which is quite quickly the following year already. So it's really remarkable kind of detection. So now we're going to talk about these phase transitions in the early universe. So now we know that there are 4 basic interactions in the universe. There's the strong, weak, electromagnetic, gravitational, and that's it basically. The strong force sticks with what like keeps things together. So protons and neutrons, the building blocks of atoms, those are made of even smaller particles called quarks. And the strong force is what keeps them together. So really it's what keeps everything together in that sense. The weak force take care of nuclear decay. And then we also have the electromagnetic interaction, which really, I mean, I couldn't be here if it didn't exist. And the gravitational is the one where you can see the apple falling from the tree to the ground. So we have 3 forces. However, in the early universe, we could actually witness only 3 of these. So we had gravity, strong, and electroweak force, where the weak and electromagnetic force merge in together and become unified, so it's one single force. And we know that this has happened. And then what is called the electroweak phase transition is what separates these 2 forces like we see them today. So phase transition is just liquid going to a solid, so like water freezing or something like that. This is just the cosmological equivalent of that. Then if we add to the mix the strong force to the electroweak one, we get something called grand unified theories, or rather guts, because physicists are yet again brilliant at naming things, so we call them guts. These are something that we are not so sure about. We hope that it would happen, but we don't have any evidence of this yet. Then we also have gravity that is really just doing its own thing. It's a bit of a problem child at the moment. But if we could unify it with the grand unified theories, so the gravity would merge in together with the rest of the forces, we would call it the theory of everything, which I think at least rings a bell in the name of the movie about Stephen Hawking. So I want you to remember 2 things from this slide: the existence of the electroweak and the grand unified theories or guts, because I'm going to talk about them later on. So what is a ground state? The universe is very lazy. It wants to go to the lowest possible energy state, where it's stable and everything is nice. So here we have Diana, the diamond, who wants to go to the couch state. Eventually, she will get there and be on the stable ground state and remain there forever, hopefully. But this is kind of also the principle of least action. We want to do things in a way that is takes the least amount of energy. So in that sense, the universe is much like us, really. So those are the 3 concepts that I wanted you to understand before I move forward to bubbles. So this is the first quirk in the universe, and this is something that is born from the electroweak phase transition, possibly. So in the beginning, we have this hot plasma soup, a bowl of it here. And as our soup bowl starts to cool down, it crosses some temperature, like water starts to boil at 100 Celsius. So does our phase transition happen at some certain temperature, and that creates these bubbles. So Diana the diamond has fallen to a lower energy state, let's say so, but actually it is not the lowest possible one. There is something that is even lower, but she just doesn't know it yet. Eventually, she will get enough energy to kind of jump over the peak and end up on the valley here to the true vacuum state. These are called, in physics terms, false vacuum and true vacuum, because yet again, physicists are terrible at naming things, and this refers to the kind of only the vacuum energy existing in that state. So the universe cools down, the phase transition happens, and eventually a Diana here will end up in the true vacuum state. Because the universe is so big, it has no way of knowing what phases have already reached the true vacuum. So you get these patches where you have the true vacuum state, bubbles, that kind of nuclei, and they start existing and then they start spreading, and eventually they will collide with each other. And this collision is something that creates, or could create possibly, gravitational waves. These collisions in the bubble collisions in the early universe plasma also source turbulence in the plasma. So if you have ever taken a plane, there's always, turbulence. It's not very nice. So the same kind of principle applies here. These bubbles create turbulence in the surrounding plasma. And that could also source the gravitational waves. Here are some simulation figures from an early universe simulation of bubbles. So here you can see them colliding. The colors they symbolize the energy. So the blue is actually the higher energy, and then the red is kind of like the lower one. So you can see these colliding and creating like these little pockets here and so on. So why are we interested in this to begin with? Like, sounds great and nice, but why? Well, it can be an important mechanism for baryogenesis, and baryogenesis is just a fancy word for why there is more matter in the universe than antimatter. So essentially, antimatter is matter's evil twin, and when antimatter meets matter, it will annihilate and cease to exist. At some point in the universe, we don't know why, there has been more matter, which is why there's now so much stuff around us. But if that wasn't the case, and we actually had equal parts of antimatter and matter, they would just eventually annihilate and there would be nothing. So it's quite nice that there was more matter at some point in the universe, so we can be here today. The other thing is that the electric phase transition, there is something in the most well-known theory in physics called the standard model of particle physics, which describes our universe. It's the best theory we have, but it's incomplete. It doesn't explain things like dark energy, dark matter. It doesn't explain this baryogenesis here. So we have to look something beyond the standard model in order to understand our universe better. So one place to look for like new physics that could emerge is this electroweak phase transition and the gravitational waves it could produce. So it's something that if we see a signal from these, we could say something new about our universe. Bear in mind that these gravitational waves have traveled for a long time. They are created in the very early, like very first second of the universe. So they have traveled for a long time. It's not like two black holes that are colliding and it creates like this blip signal and it's gone, but rather it's like a background gravitational wave effect, because they have been hit there for so long. So it's not one signal, it's rather a continuous one. And there's a lot of other stuff on top of it. So what about cosmic strings? Let's get back to the first question, to the question that I asked in the beginning. So what are cosmic strings? Well, the title kind of spoils it rather, doesn't it? They are topological defects. And you might be asking, well, what are topological defects? Usually people use this following analogy when they discuss them for the first time. So imagine that you are standing on the shore of a lake and you can watch as it freezes over very slowly. It doesn't freeze over just continuously, but rather you see different ice patches emerging. And eventually these ice patches will meet and merge together, but there will always be sort of like fracture in the ice that you can see. So it's not like a continuous smooth block of ice, but rather a patchwork of different ice sheets together. So that little fracture that you can see on the ice, that would be the topological defect if we were talking about like cosmic things. You can also study these topological defects in a lab. So you have liquid crystals. A liquid crystal is just really a crystal that has both liquid and solid phase, kind of. So you have a crystal and the molecules inside the crystal can move like a liquid. And because of that, you get these really curious looking patterns when the phase transition happens. So you can see here kind of these like string-like formations that go in the crystal. And this is essentially what cosmic strings are, but just the cosmological, a bit more complex equivalent of that. And unfortunately, you can't study these cosmic strings in a lab, but they do exist in like real life as well, and they are not just some mathematical concept. In the more universe context, we have 4 kinds of topological defects. We have domain walls, cosmic strings, magnetic monopoles, and textures. I'm going to briefly introduce you to domain walls, how they work, because it's the simplest example one can give. And then we're going to move to cosmic strings, and then finally to magnetic monopoles. But you might also be wondering, well, what on earth does topological mean? Well, topology is a branch of mathematics which essentially can help you understand why a donut and a coffee mug are topologically the same. So you can form that donut shape you see here, and you can just kind of take a piece of clay, start from a donut, and end up in a coffee mug. So in mathematical sense, they are the same object. You can sort of like understand it that like how a geometric object behaves when you try to deform it, stretch, twist, crumple it, bend it, sort of that kind of things. And that is a branch of mathematics that I found myself at least quite complicated. We're also going to talk about breaking the symmetry of the universe. So symmetries are quite nice, or at least I'm a physicist, so I find them really nice. But you can think of them as like, you have a square and you rotate it by 90 degrees, it is the same square again. And these symmetries are also present in the universe in a bit more complex terms, but they do still exist, and they can be, and they will be broken. And these symmetries can be broken in phase transitions. So we are going to go back to Diana the Diamond and talk about these domain walls. So Diana the Diamond is standing on top of the hill. She has 2 options, either fall to the left or to the right. And depending where she falls, she gets a little bit different orientation on the side that she falls to. So in order to get from here to here, you need to cross this hill. And this is the basic idea behind a domain wall. It's a bit like, imagine this. So in Europe and in the UK, we drive on the, well, the UK drives on the wrong side of the road, in my opinion, and the rest of the Europe on the right side. But at the cross, or the border of France, you eventually have to switch. So there's this narrow border where you have to switch the regulations, which countries' regulations you follow. And that's kind of a domain wall, really. But in the more cosmological sense, you have different orientations that you can fall to, but you always have to cross this high peak area. Because the universe is so vast, so there's different regions again in space, and they can fall into different regions or different orientations, because the information doesn't pass that quickly. It is the speed of light. If you are further than that, the universe has no way of knowing which orientation the other parts of the universe have fallen. So you get these, in order to get continuous kind of map again, you have to cross this peak here. So this purple area will extend until it tries to bump into this green one, but it has to create this kind of domain wall between these 2 orientations of the same phase to make it continuous and smooth. So now we get to the cosmic strings. I think I should answer one of the quiz questions here now. So cosmic strings aren't really string theoretical at all. There is nothing inherently string theoretical about them. They just have a very confusing name. However, they can be in some string theoretical solutions, they can also be there, but then I believe they are called something like superstrings or something like that. So it's a bit different, different thing. But these cosmic strings, they are thin and line-like. So they are very thin and dense objects. So option number A in the poll was right as well. Only really the cosmic yarn one was incorrect. So if you voted for any of the other three, you were correct in some manner. So they form these little networks of strings, and you can kind of see it here. They loop around and they can eventually kind of cross with each other and chop each other off in that way and get these little loops that will then radiate, oscillate, and decay. And these little loops that you see here you can see it crossing itself, for example, and this little loop gets free. And this loop is then what sources gravitational waves from cosmic strings. So the usual reason why we're looking at cosmic strings is, well, our best physics model is incomplete, the standard model that I mentioned earlier. And the other thing is that those grand unified theories, so the GUTs again, they have cosmic string solutions. So the original idea behind cosmic strings was, well, maybe it could help us explain galaxy formation. Unfortunately, that's not the case. The cosmic microwave background, so the first light from the universe, essentially disproved this assumption. But there is still interest in this area of research because they are, the GUTs have these cosmic string solutions, and there is now also the possibility of the gravitational wave background emission from these little loops. So if the domain wall example confused you, this cosmic string one will confuse you even further, because instead of like two options where we can fall to, now we have a whole rim of the hat here. So we start in the high energy phase here, and then our ball can roll anywhere on the rim of our hat, or valley, if you want to call it that. And depending where on the valley or the rim of the hat it falls, it's again on different angle or different orientation slightly. So in order to make this space continuous, it has to pass through this area of high energy. So these are very dense objects that are kind of like 2D lines. And actually, funny thing is, this is also in popular culture. You can, if you are a fan of Star Trek, you can watch the episode Telos from season 4, episode 10 from The Next Generation. I haven't seen this personally, so I can take no responsibility if it is actually scientifically accurate or any good. So watch at your own responsibility. But if you're interested, there's a Star Trek episode about this. So those are cosmic strings. What about magnetic monopoles? So what is a magnetic monopole? So as you all know, we have magnets that have the South Pole and the North Pole. Is there any reason why we couldn't just cut this in half and have a singular pole, so either North or a South Pole for a magnet? Well, there isn't really any theoretical reason why not. The classical electromagnetism that was formulated by James Clerk Maxwell in 1864 describes essentially how electricity and magnetism work and how they work together. But the thing is that while single charges, so you can have a plus or minus charge in electricity, those can exist. Magnetic charges cannot exist alone. They always have to come in pairs. But there is no reason why this has to be the case in like theoretical standpoint. In fact, it would actually make the whole theory more beautiful because it would make it symmetrical again. we have plus and minus charges that can exist. Why can't we have a north and a south pole that can exist alone? So it's quite interesting why we cannot, or we haven't been able to see any of these magnetic monopoles as of yet. So these are actually also potentially created in the early universe in the grand unified theories. So the guts come back again. They have monopole solutions. And these monopoles are very stable. So if they existed from the early universe times, they should still be present, because unlike other particles like the Higgs, it doesn't decay. So they should still exist unless they have annihilated with each other. So one reason why we haven't seen any is that inflation could have deleted the amount of magnetic monopoles that we had in the early universe. So inflation was the rapid expansion of the universe at the very start. So that could have kind of deleted the amount of monopoles we had, and they would be so far and like far apart and just a few here or there, it would be rather impossible to detect them. So that's one solution. This is something called a monopole problem, actually, that inflation has kind of explained or tries to explain as well. So these magnetic monopoles can actually also exist together with cosmic strings. So you get these like necklace configurations. So you have these red or orange rather magnetic monopoles, and then the cosmic strings kind of thread them into these necklace configurations. And here you can see a decaying network of cosmic strings and magnetic monopoles. So you start very dense, and then slowly your network starts to decay as it radiates gravitational waves and so on. It's also very good that this network decays, because otherwise we couldn't explain why there aren't a lot of cosmic strings crossing the sky, for example. But we haven't seen any cosmic strings either, so it's good that the kind of network slowly disappears as the universe goes on. So one final kind of quirk that I want to mention today, this is a bit shorter one than the others, are primordial black holes. And just to recap what black holes are before we delve into what primordial black hole is, we are going to just briefly recap what these actually are. So here we have a picture of a black hole from the Event Horizon Telescope. You can see all of like gas and dust and particles around here, because of course you cannot take a picture of black hole because there's no light that can escape it. So rather we have to look at something that surrounds it. So black holes are extremely dense objects with no escape, not even for light, and event horizon is the point of no return. Here you can see a simulated picture of a black hole. It's very kind of crisp and nice looking. And black holes are formed by dying stars that collapse under their own weight. So for some reason, there's a common misconception that black holes are these sort of like cosmic vacuums, that they kind of eventually suck everything out of the universe, no matter how far. This is obviously not the case. Quite glad that it isn't the case, because eventually there would be nothing in that case. So only if you go too close, essentially, to the event horizon, do you actually have to worry about not being able to get back to the world of the living. So what are primordial black holes? So primordial means that it came to existence shortly after the Big Bang, or actually already Big Bang again with the quotation marks. It's born from high density areas in the particle porridge or the particle soup. So it's again the hot plasma soup. And you have more dense areas in the plasma soup. They kind of clump together, and then those dense areas, they could potentially collapse under their own weight, and you would get these primordial black holes. These can actually be very tiny compared to regular black holes, and their mass can range from 10 to 15, so quite many zeros there, up to 10 to 50 kilograms. So they are very dense, again, as black holes tend to be. So why are primordial black holes interesting then? Well, one reason is, again, gravitational waves, but the other one is that they could be a dark matter candidate. So as we know, only 4.9% of the matter, of the things in the universe are actually normal matter. Then we have the dark energy and dark matter, which we call that because we don't really know what they are and we can't optically observe them. So they are in that sense dark to us. So primordial black holes have been suggested to be one solution or one potential solution to dark matter. But we will see what actually is the solution at some point in the future, I hope. So can we actually detect the signal from any of these quirks that I just mentioned? So we had the bubbles, cosmic strings, and magnetic monopoles, and then finally the primordial black holes. Well, current and future experiments to detect these phenomena exist. We are going to talk about LISA, which stands for Laser Interferometer Space Antenna, which is an upcoming mission. So we are going to talk about that a bit more in detail. Then we also have pulsar timing arrays that have set constraint on cosmic strings. Pulsar timing arrays are these pulsars that I mentioned earlier. So those rapidly spinning neutron stars that are like the cosmic lighthouses of the universe because they radiate the light beam, and you can detect that. So pulsar timing arrays use those pulsars as kind of cosmic clocks to time how a gravitational wave would travel. Then we have metal. They always silent, apparently, because physicists are yet again terrible at naming things, which stands for the monopole and exotics detector at the LHC. For those of you who don't know, LHC stands for Large Hadron Collider, which is a particle collider at CERN. So CERN is the center of particle physics in Switzerland and France. There's this huge particle collider underground with multiple detectors. So metal is one of them. But this detector cannot detect the monopoles that I just talked about. This is a different kind of flavor of monopoles that it could potentially see. It hasn't yet, at least, but just not to confuse those like early universe magnetic monopoles from like GUTS, the grand unified theories. This is not something that aims to detect them. And then finally, we have SKA, which is the square kilometer array. It's a radio telescope park. So it consists of many radio telescopes scattered across the world. I think it's an upcoming thing as well. And then there's quite many other experiments that could help us to narrow down the range for primordial black holes. But as I promised in the start, we should talk a bit more about laser interferometry, and now is the time for that. So what is it? Why do we need it? And what does it have to do with LISA? So as we know, as a gravitational wave passes, it stretches the space-time. So these 2 points here would get further apart. How do we measure this stretch of the space-time? What is always standard, a constant that doesn't change? The answer is the speed of light. So we can use light, or lasers in this case, to measure how much the fabric of the space-time has stretched. So here we have a laser that shoots a laser beam here to the beam splitter. The beam then splits into two. So it travels with this arm to the mirror, bounces back and goes to the detector, and to the mirror and back again. However, when we have a gravitational wave passing through, it stretches this situation a bit. So this arm actually gets squeezed in if the gravitational wave is passing from here, and this one stretches out. So now the timing that the light has to travel is longer on this stretched part of the arm. So these beams that turn around at the mirrors and go for the detector would arrive at slightly tiny bit different times, and that time difference is essentially what tells us if there has been a gravitational wave or not. Now you can imagine this will be a really delicate experiment, And LIGO is actually a ground-based laser interferometer. So this is actually a schematic for LIGO, how it works. And the thing is that you can't build that big of a detector on Earth because we have, well, limitations how big it can be. And there's also things like the Earth moving, lightning strikes, a truck driving nearby that kind of introduce noise to the system. So the option is now to go to space. And that's what LISA does. So LISA will be the first, but hopefully not the last, space-based gravitational wave detector. It's a project with ESA and NASA. So it is a joint project. And it's this like equilateral triangle, which has 3 spacecraft in each corner. And each of these sides of the triangle, so the distance from here, one spacecraft to the other, is called an arm. The arm length of this, so the distance between these two, is 2.5 million kilometers. So roughly 6 to 7 times the distance from Earth to the moon. So this is the reason why we can't put this on Earth, because, well, it's quite big. So the launch will hopefully be in the early 2030s. I believe the current year is 36. Hopefully it doesn't get delayed, like usually space missions do. But LISA travels on the orbit around the sun with the Earth, so it trails behind it. Here you can see the orbit around the sun. So it kind of rotates around, and you can think of this as actually having 6 lasers instead of these 3 here. And by the way, you won't actually see red lasers in space. This is just for visualization purposes. This is not Star Wars, unfortunately. So no cool lasers for us. But there is one incoming and one outbound kind of laser going on. So there's essentially kind of 6 arms instead of 3. So the possible gravitational wave sources, besides these like cosmological ones that I mentioned, are massive black holes and extreme mass ratio in spirals. And that word is just a fancy way of saying you have a very small thing and a very big thing orbiting around each other that just will eventually collide with each other. So these are kind of the more like, so the gravitational waves from the early universe, they are kind of the background noise in the detector. And these massive black holes and other astrophysics sources are more of the like foreground sources that would also introduce noise to our system. So our question is basically, how do we essentially get rid of these foreground noises to get to the gravitational wave background from these very early universe gravitational waves? And that is essentially what the LISA cosmology working group is working on at the moment. How do we get the noise out of the way so we can actually possibly narrow down, okay, what are we seeing? Is this gravitational wave background from cosmic strings, from the bubbles, from the electric phase transition, or from something else entirely? And if this video works, let's see, hopefully. Here you can see the LISA orbiting around the Earth. So here we have Earth going on, and then you can see the gravitational wave passing. So hopefully we will get to see LISA soon. And there are also other space-based gravitational wave detectors coming. And finally, to my conclusions. So early universe is an interesting area of research, with many phenomena, which I only told you about a fraction of them due to the time limit, unfortunately. And hopefully these gravitational wave signals actually could be something that we could detect. And this would help us narrow down kind of what is the next theory after the standard model that explains our universe very well and what it knows. So like interactions and how things get mass. but all the other stuff that I mentioned, like the dark energy, dark matter, are still a complete mystery. So hopefully these gravitational waves from the early universe could help us narrow down the kind of group of theories that exists, and we could move forward from the standard model. I think that's that. Thank you, and you can contact me at my email address and questions.